when in reality, that's how it works when we go face to face. You know, I get out of class. Usually Michael's the same way. And Greg, I think, has been looking at his phone on the way down the elevator shaft. And so that's kind of how we put our ideas together on a normal Friday. So there's nothing at all unusual about that.
Exactly. Well, if you've been in a 452 weather discussion, you know you got to be ready by 3:45. So
that's right.
I'm still used to timeliness.
Are you going into the office regularly yet, John?
No, but I'm hoping. I got my second vaccination yesterday. So I'm hoping that the summertime I'm going to be in there working every day, because I can't wait to be, availed of more than one machine and various other nice benefits of that. So that's what I'm hoping for.
Yeah.
Hi, Angela.
Hi.
Hey.
Hi, Angela.
Hello. I just have so many things running on my computer. Hopefully things don't crash again. I'm trying to run everything. There's so many good loops to show. So we'll see if we can constrain this a little bit. Are you guys waiting on me? Are we ready to get started?
You're ready to go. The stream is going, the recording is going, and you should be able to share. So we should be good to go.
Okay, let me get this sorted. I think I'm going to share my whole screen, because I'm going to go back and forth between things. So let me. All right, can you see my screen now?
Yeah.
Yep.
Okay, great. All right, we're going to get started. So I admittedly didn't have as much time to look at this event as I did the last week. In 453 Lab, weather briefing was kind of touching on what the forecast was for this event. So I'm going to try to summarize a little bit about the big picture and some of the earlier storms that developed, and then I'm going to pass the torch to Andrew, who's going to focus in on one of the later events. So for those who aren't aware, yesterday was a rough day in the Southeast, and a week of so much loss, it's really hard to see that there's more. So there were roughly three long-lived tornadoes from the early reports, and this can always change. This will be updated as more reports are finalized and damage surveys are conducted. But as of this morning, you can see it was primarily focused in central Alabama, with a few tracking into Georgia. And unfortunately, as of yesterday, there were 5 fatalities associated with one of these tornadoes. So it was interesting because the conditions, which I'll show, were extremely favorable, absolutely warranting a high risk from the Storm Prediction Center. So this was the Spc Outlook that was issued on 12Z yesterday morning, to go through the 24-hour to 12Z this morning. So you can see the high risk was focused a little bit more towards the northwest in the initial thought. The actual reports kind of fell outside of that main high risk zone, but this was still alerted with a long period of time, the alert that this is going to be a big event with the potential for long track tornadoes over this area. So that they actually did update the high risk location at 20Z. And you can see this reflects the shift a little bit more into Arizona. So, we could get into the weeds a little bit on exactly, where things set up relative to where the tornadoes formed. But overall, giving the heads up about this high risk in northern and central Alabama was certainly warranted. So then if we just look at the tornado probabilities, again, this, the high 30%. So for those who don't look at this as frequently, this is a really high percentage. So that they have high confidence in tornadoes for this period. Oops. Okay, so just to start off, so this starts off at 12Z yesterday, and what this is showing is the terrain is the color shading that's kind of in the background here, and this will show the surface observations and the surface fronts. So earlier yesterday morning, there was actually quite a bit of mostly elevated convection occurring kind of north of this warm front over northern Alabama into Tennessee. I don't have the radar overlaid here, but that was where most of that was concentrated in the morning. And you can see that reflected in the surface observations with the rain in northern Alabama. So if we move forward 6 hours, you can see the warm front moving a bit northward. You can see dew points are already in the upper 60s. And then now so we're going to 21Z. Again, we see this warm front situated over northern Alabama. And again, you just have the strong southerly flow, dew points now hitting 70 degrees Fahrenheit in central Alabama, and then continuing on into 0Z as this cold front moves forward, and you can see the warm front extending much further northward. And Andrew will talk a little bit about this, but one of the things you'll notice if we go back now, you focus on the low pressure system. The low pressure as it moves northeastward also is deepening significantly. So we see this increase in the warm, moist air extending northward into the Tennessee Valley. So this is reflected, this is looking at 12, 18, 21, again in 0Z at the same times. What's plotted here is the surface pressure in black, the temperature is seen in red, and the dew point is what's being shaded. So the colors start in the upper 50s. So the high 60s, 70 degree dew points are reflected in this light green color. So this is just showing in a different way what I showed last time, this progression where you see this deepening low in the Tennessee Valley and these very warm, moist air extending even further northward in this corridor in this warm sector. So 500 millibars, this is now at 12Z on yesterday morning and then 0Z. And what's plotted here are the heights in the black. You see the wind barbs. The temperature is the red contours, and the wind is what's being shaded. So you'll notice there's a long wave trough extending off into the central U.S. And really, it's the short waves that are being injected over this region. Large amounts of variclinicity. I'm not going to go too much into this as what happens at 0Z and forward, because Andrew's going to talk a little bit more about this. But you can also see the winds, especially by 0Z. These contours are 90 plus over the Tennessee Valley. So now I'm just going further up. This is now 300 millibars, and this is at 18Z yesterday, so in between the last two plots. And I just really want to point out here the jet streak, which is on these purplish colors are greater than 120 knots. So you can see that extending here over into the southeast, and you can see the pink contours here are the upper level divergence situated over the southeast. So let's move back to the surface. So I'm showing here that at 12Z and 18Z, the surface-based CAPE, because if we're going to be thinking about tornado genesis, we want to think about, and supercells, we want to think about what is a surface parcel going to be doing. So we'll also consider the surface-based SIN, which is what's colored here in the shaded. So the SIN is shaded, the CAPE is the red contours. So early on, we see most of the CAPE concentrated now down near the Gulf Coast and considerable amounts of SIN out ahead. But as we'll notice with daytime heating, and we've got the precipitation stayed mostly to the north of that one front that had occurred earlier in the morning. You can see most of this area in the Mississippi, Alabama area has surface-based CAPE values exceeding 2,500 or 3,000 joules per kilogram. So plenty of instability from the surface-based parcels. So I just want to show a few soundings, and they're going to be working eastward. So we'll start off in eastern Louisiana. We'll move to Jacksonville, Mississippi, and then finally look at the morning sounding for Birmingham, Alabama. And all of these, there's so much detail we could go into, but just very broadly, a few things to point out. Here we can see the reflection of the surface-based cape, even early in the morning with very high values, most unstable, exceeding 3,000 joules per kilogram. Another thing we can think about is the mid-level lapse rate. So you can see this elevated mixed layer where the lapse rates in the morning are over 7 degrees per kilometer, and lifted indices, -7. So this is, you've got not only the surface-based instability, but you can see these really steep mid-level lapse rates. And then winds are the big thing this day as well, in terms of you can see the vertical wind shear. So you can see this represented in the hodograph, or if you want to look here at the wind bars. Here's a signature of the there was a low-level jet, broad low-level jet earlier in the morning over the southeast part of the U.S. You can see here about 50 knots, and you can see the turning of the winds as we move along. So deep layer shear, effective shear values were quite high, and we'll compare this as we go eastward and then with time as well. And then the storm relative velocities, which is what we want to look for in thinking about, in the low levels, are we going to see in the lowest levels these backing of the winds that would support tornadogenesis are quite high as well. And the other parameters, there's so much valuable information on here. So a couple other things to point out here is there's as I mentioned last week, there's several parameters that are derived from these different measures of instability and shear that will give you some sort of threshold to consider of the likelihood of supercells, or in the case of a significant tornado parameter. So this shows kind of what you would expect for if you're going to get a tornado. You would expect this tornadic parameter to be roughly above 1, and then you can see how drastically this increases with intensity of the tornado. So even this early on, you can see these values of 6 to 10, depending on which layer you calculate these parameters, which would indicate significant tornadoes in this region. So again, let's just keep moving very quickly eastward. So now we're looking at Jackson, Mississippi. And now we're seeing really a similar story in terms of just broadly large amounts of cape. There is still some considerable sin. This is again really early in the morning. You can see the strong turning of the winds. Just deep layer shear, lots of instability, similar story, steep mid-level lapse rates. You can really see that well-mixed layer, elevated mixed layer here in this layer. And then, Birmingham, as I mentioned, early in the morning, there was precipitation over that area just out ahead of that warm front. So that's being reflected here in the saturated layer. And you can see the steep mid-lapse rates aloft as well, and the large amounts of turning and the low-level winds in this area. Okay, so how is this going to evolve throughout the day? So that was all the soundings at 12Z. So if we put all of this together, earlier in the morning, there's a mesoscale discussion from the Storm Prediction Center that's really highlighting this initiation zone occurring in this warm sector. So, you could have some storms continuing to form along the warm front, some along the cold front, and then there's just really unstable air, moist, unstable air in this warm sector. So their particular forecast was thinking about around 17Z or so as the initiation time from some of the heating, and a lot of this early morning precipitation was extended mostly to over northern Alabama and northward. So unsurprisingly, there was a tornado watch that was issued shortly thereafter. So it was issued effective from 11 a.m. local time until 8 o'clock at night. And as this case warranted, given the parameters we just discussed, a particularly dangerous situation indeed was issued. So in addition to numerous tornadoes, including the possibility of intense long-lived tornadoes, widespread wind damage, and there were some left mover hail producing storms kind of in northern Mississippi. I'm not going to spend too much time talking about that because I didn't get to look into a whole lot of detail, but there were some hail reports in northern Mississippi from some of these left movers. All right, so just diving in now we're getting around that 17Z. So this is around the time when it was forecasted for a rough initiation. And you can see from the radar, there are some cells that had already popped up over the region. Dew points again, where we've got 70, 71, 72 dew points, such a warm, moist air mass coming on shore in this lower Mississippi, Alabama region, extending into central Alabama. So what this plot shows now is the change in theta E over 3 hours. So you can see over the course from, before 17Z, so 14Z leading up to 17Z, you can see the large amount of increase in theta E. So you're just warming and moistening this area over central Alabama, especially. And then if we similarly look at the 3 hour change in the mixed layer CAPE, it's also reflected here in the 3 hour time period, CAPE increasing by 1,000 joules per kilogram here, especially over central Alabama, with the SIN largely eliminated here in this central region. And then also, so by the time we get to 17Z, we had all of that moistening, we had that increased instability, and this shows the mean parcel lifting condensation level height, so LCL, in meters above ground level. So here we've got these pockets of relatively low 500 meter LCL. So you've got this moistening, you've got the lowering LCL. All of this is setting the stage for not only convective initiation, but in supporting deep convective activity over this region. I don't know why this cut off, but this is the mid-level lapse rates. So again, it's just still reflecting those very steep mid-level lapse rates across this region with that elevated mixed layer. But really a big key of this day too was also the shear. So what this is showing here is the effective bulk shear and not. So this is 18Z, this is at 22Z now. So now I'm gonna kind of hone in on a few times that we're seeing a lot of these, we end up seeing a lot of these long track supercells. So basically what you're seeing here in the blue contours are the values of this. And I posted this last week as well in terms of what do these values mean in terms of what we would expect in terms of, tornadic supercells. So if we think about this effective bulk layer shear, so this is kind of really strong deep layer shear, 60, 70, 80. I mean, this is well in the upper limits of upper part of the statistics of what we would expect for significant tornadoes in this area. So it's really interesting, and I'll show this a little bit later in the radar and satellite loops, but these were really long-lived supercells, cyclic supercells, just very deep layer shear over this whole region, starting in eastern Mississippi into central and eastern Alabama. So that's kind of the bulk shear over a deeper layer. So what this plot is showing, so this is again at 18Z, this is at 22Z. I ended up cutting off the label here, but what you see, what is showing now in the blue contours instead of the effective bulk shear is now we're looking at the effective storm relative helicity. So where in the low levels are we going to have roughly the levels will we see that backing of the wind and the helicity necessary to actually spin up a tornado from these long-lived cyclic supercells that are, at this time were propagating across the region. So if we look at this roughly, you can see higher values, 300, 400, over this kind of central Alabama region, extending over into Georgia with time. And the wind barbs here are the storm motion and knots. So you can see too, these are, 40, 45, 50 knots. So these storms are, also just screaming across this area. So really high storm motion as well. So if we put kind of all of that together and we think about how that significant tornado parameter evolved throughout the day. So it was already quite high in some regions and some of the earlier soundings. So by 18Z, if we look at that parameter, which remember anything greater than 1 is indicative likely of a tornado, and then so these higher values are getting more into EF3 plus, you see with time, you can see these corridors of high, of this parameter quite high, 3 or 4 into central Alabama during this time. So this is, a lot into the weeds, but really showing just the support in terms of the instability and the shear, both the bulk layer and thinking about the storm relative helicity and how we're going to support these intense, deep, long-lived supercells and the potential for tornadoes. So Birmingham, this is this is just a little bit north along the edge of where a lot of the most favorable conditions were. But there was indeed the first tornadic supercell just went just south of Birmingham. So if we look at the Birmingham sounding at 0Z, I mean, you can just see the just deep layer of cape that's available. We've got, this high supercell and tornadic parameters. You can see just this really deep wind shear. I mean, this is just such a environment so conducive for this event. And I'm not going to spend too much time going into this, but you can really see the realization of that. And there's ongoing convection in this area as well. So with all this favorable environment, how did this actually evolve? Because the idea was that you'd probably have more discrete cells developing in that warm sector, but really you've got all this deep layer shear. That you worry about how many are there going to be? Are they going to interfere with each other? Are they going to be more clustered? With as moist as it was, maybe the cold pools won't mess up the environment for a storm that's nearby if it's so moist. But there's a lot of detail here in trying to understand exactly how these will evolve.
Hey, Angela?
Yeah, John.
On that sounding, did you guys get a chance in class to look at how a series of soundings at roughly in Birmingham evolved over a period of time? Because this is an unbelievable, you're catching it red-handed with this extraordinarily deep layer of free convection, and the shear is right. Did it start out that way, like say 12 or 30, 20, 24, 36 hours earlier? Was there an elevated mixed layer or something on top at one point?
Yeah, so here's the Birmingham sounding at 12Z. So you do see, I mean, there was ongoing precipitation at this time. Yeah. But you can really see the steep layers. But if you also look, just a little bit west over Jacksonville,
wow.
I mean, yeah, you can see the elevated mixed layer. I mean, it's just, it doesn't get more kind of classic than this.
No. And it really gives you an insight into what must have happened between Jackson and Birmingham over a period of time to just get rid of the inversion and moisten the mid layer. And wow, did it go crazy? That's awesome.
It is. Yeah, this, I've only gotten to look at this a really short period of time, but I'm putting this in my back pocket to analyze a lot more later. This is an incredible event. And so thanks to Andrew for pointing me out to this. I really don't like showing, damage pictures and that kind of thing, but I do really want to show, like, man, tornadoes in the Southeast are a challenge. You've got, I mean, it's so moist. A lot of times these can be obscured. There's so much vegetation and rolling hills. Like, as someone who, I don't know, there's probably quite a few on here who've liked to chase or chased in the past. Like, I can't imagine trying to look for these in Southeast Alabama. And it's so challenging, but, you can see all the vegetation in the hills. And but here's just one example of, and this is the tornado I want to focus a little bit in on, because this was unbelievable. So,
Angela, real quick, that's interesting you bring that up, because I said something right before we started about how chasing in the Southeast can just be a death wish. For many reasons, just like this. And you can see, this person must have been at home when they took this photo, and they're just perfectly positioned kind of right in the notch of the supercell. You can just tell, right? Because to the left of the image, you can tell you have the rear flank basically wrapping right around this tornado. Heavy rain, hail. You don't have a chance of seeing this thing if you're behind it. And you can tell out in front, you have cloud bases that are probably no higher than 500 meters. So, I mean, yesterday, the thermodynamic environment was so incredibly supportive on top of the wind shear and the kinematics that with these things moving as fast as they were, you probably didn't see this for much more than a minute or two before it was there and gone. And as a chaser with that kind of terrain, that's just incredibly dangerous, because this is such a violent tornado that's just basically hiding, and you see it for 1 to 2 minutes. And if you're in the path of that thing, it's too late once you see it. It really is.
Yeah, thanks for elaborating on that, because it's terrifying. And like I didn't see a lot of Twitter yesterday, but I always kind of keep a track of some of the usual suspects, from some of the chasers and who was out, and there were some things that were really concerning. So I really hope that everybody was okay. This is a rough one. So I want to show some satellite images, but so there was roughly 3, as far as I know, kind of long track tornadoes. So there was the one that went over just south of Birmingham, and we were watching because I was wondering if it was going to actually hit the radar. Like, it's just so many of these go so close to it. So just watching the circulation go just south of the Birmingham radar. And this was the second one. So this was I think Andrew and I were referring to this, the Centerville, I don't know what they call it, Centerville Brent. I don't know where exactly this was taken, but this was that one, that tornado. And then there was a third one that Andrew's going to talk a little bit more about. So let me switch over here to some satellite loops. So hopefully this all doesn't crash and burn. So this movie, this is showing the GOES infrared. We're starting at 17Z. So this was when things were forecasted to initiate. So things were already kind of ongoing, already had started firing up before this time. So this loop goes from 17 to 0Z to try to really encompass the time that I've been focusing on before I pass it on to Andrew. So you can already see there's ongoing convective activity. You've got a lot of these initiating kind of in southeast Mississippi, and you can see the presence of a more discrete one over west central Alabama. So let me just play this loop. Oh, hold on, it's got to run through it a couple times. Give me a second. Should have just left it going, but I was afraid my computer would crash. I'm not sure why it's not going. Maybe it'll need to take another round here. So while it's trying to figure out what's going on here, you'll notice, there's a lot more widespread precipitation that's occurring out ahead of the warm front with time. And then you'll see that all of this is firing up in the, I don't know why this isn't looping, right? That's annoying. Maybe I just need to, okay, hopefully this doesn't crash the whole thing. Let's see what happens. I really like this slider, except that it just uses so much to be able to load it. Okay, well, let me come back to that because I know the radar loop will work. So the radar loops also starts, this actually starts a little bit earlier. I started this loop at 16Z. So you can already see there's a lot of ongoing stuff, kind of a mess of precipitation further northward. But just really focus and key in here on this area, especially in central Alabama. So let me play this. So one of the things you'll notice, so here, I mean, here's this beautiful, you could see the V-notch, this beautiful isolate cell, but I mean, there's just stuff going up everywhere, and it's kind of clustered, and there's such a large amount of shear that, yeah, these things are just firing up everywhere in close proximity, and it gets messy. So let me have you hone in on a few more things. So watch, I'm assuming you can see my mouse, watch this guy here. As we go forward, and this is this long track supercell, long-lived supercell that moved just south of south of the Birmingham area. This is a mess. So there weren't a lot of these discrete cells, but the supercells that did form, they were on the ground for hours and producing tornadoes, with a few of them producing tornadoes. So it's hard to go into a lot of the weeds in this kind of regional composite. So I'll dive into one of the radar. Let me see if this, okay, so now it loaded. So you can see this reflected quite well here, as well as we go forward in time. So really cold cloud tops. You can see more of these discrete ones. You can see more of these that were clustered later on. But you can see just really the really deep, intense updrafts with time. And, you kind of have to pick one to follow. But you can see the long tracking of these cyclic storms as they move eastward. So if you look now at this last one, kind of this most westward one, you can track this all the way from Mississippi across Alabama, going into Georgia, and that's where Andrew's going to talk about that particular one. But let me just zoom in. Now let's see if this works. So this is 22Z. This is the 1 minute mesoscale sector, the visible, and you just can get a little bit more into the weeds if it loads. Yeah, so man, there's something that's just so awesome about seeing the bubbling in the visible satellite loop of these.
I agree.
Of this convection. And I know I'm not going to go into too much ways. I know I saw a few above anvil cirrus plumes earlier, but there's so much to dive into, and I don't want to go too much. And then you can also just really see the strong southerly flow kind of streaming up from the south and the cloud streets here as well. So very finally, and this is the part that made my jaw drop, is the radar loop from the second Launchpad Supercell. So let me go back in time a little bit. I'm way zoomed in so we can really look at some of the weeds. So let's watch as this moves into the domain. So I'm zooming way in at the hook and the radar reflectivity. This is the lowest tilt. This is the 0.5 degree elevation angle. What's being shown here is the radial velocity. Down below is the differential reflectivity, and then the correlation coefficient. And just for those who may not be as familiar, or could use a reminder, these values of correlation coefficient, actually I can show you what those values are. Hold on, wrong one. These values, are what low values, below 0.5 especially, are what you consider, clutter, definitely non-meteorological. So this is the tornado debris signature that can be followed, where, the only thing that's going to be producing such low correlation coefficient in this area of rotation is because you've got debris. And I don't have a vertical cross section to this. I didn't have time to make it, but from what did I note? That I saw someone plotted this up. This tornado debris signature extended above 20,000 feet,
Wow.
which is unreal. Like this is a violent tornado. And this tornado debris signature, I don't have the tracking on here. I had it more in real time. This debris signature was tracked for over 100 kilometers, and over an hour. You could follow this signature. So let's just go a little bit forward in time. I mean, there's so much to look at. Look at these velocities. The velocity's folding. It's so high. So just the inbounds are 140 miles per hour. I mean, and this this is above the ground. So imagine what some of that shear is going to be like below the ground. And this, I mean, these values are 0.3. I just don't know that I've seen them that. I'd have to look at the statistics of how low this has gotten. It's just jaw dropping. I mean, this is, from a radar perspective, this is one of the most amazing things to see. And then from like the human perspective, this is horrifying.
Yeah.
It's awful.
Yeah, then I know. I mean, as this tornado moved away, because it went through a rural portion of Alabama once it, tragically struck Centerville, that debris started raining out, and you could see that in the CC. You could see that the Supercell was just lofting debris, like, miles and miles around the storm. So I'm sure, there's pieces of homes and stuff that landed miles from Centerville with this updraft. I mean, like you said, it got lofted 20,000 feet. Right around this time. So I mean, that's ridiculous, unbelievable.
Yeah, I'm glad you brought that up, because I'm not going to futz around with this now, but if you zoom out, you can track, especially if you go higher into it, you can see a debris signature just way downstream. So I talked about this for a while. There's a lot to look into, but I mean, this was a long track tornado, and then as I mentioned, there was that cell that popped up in eastern Mississippi that tracks through. And this is, I think, where Andrew kind of wants to step in and talk about this more late one. So the event kept going into the night, and I'm going to stop sharing so Andrew can jump in now.
Awesome. Thank you.
Does anybody have any questions, though, I guess, before I go? I know I kind of just like talk straight through that because it's like amazing and awful. And does anybody have any comments before Andrew takes over? Oh, I saw Pete's comment about making some loops of the meso imagery. Yeah, I appreciate that. I just kind of threw this together from the slider, but yeah, those loops would be really great. Thanks, Pete.
I guess I'd only comment that the forecasts, especially the updates from during the day yesterday, were just outstanding. I mean, how this thing was coming together. And, you know, we're in an era where people don't trust the government. They don't trust science. And when you put science and the government together, you get something like the National Weather Service and the CDC. And here we got the National Weather Service, a banner day, making yet again an outstanding forecast for people who are down in these places that are under assault. So I just think that's something that needs to be celebrated somewhere. And I don't know where the right venue is, but there was no shopping necessary here to include Alabama. Alabama was warned of a real serious threat, and that threat came to be, and only a few people unfortunately died, but it could have been worse. It's amazing.
I think so too. And one of the things to overlay is kind of the types of housing in this area. So I don't know about the fatalities, but you know, I would unfortunately probably speculate that it was probably, you know, outside of town. Maybe I don't know if it was what the housing type was in that area where the fatalities occur, but that's something that I know will be looked at, and I'm sure we'll see some of the damage reports come out too. So yeah, it is incredible that there wasn't more loss of life, you know, but any is too much. And it was very well communicated. One more aside on that. I don't know how many people follow James Spann down in Alabama, but while he was reporting, I saw this after the fact. He warned his wife and found out that his property was damaged, like while he's on air, and the pro that he is just jumps right back in. And I just can't even imagine, you know, having to do that. And I
know.
Just really hats off to all the meteorologists working on this event yesterday.
Incredible.
Oh, Megan's got an update about the damage survey. So this was an EF2 damage. Oh, the Ohatchee area was where the fatalities had occurred. Thanks for that, Megan. All right, I'm going to stop tracking. Andrew, go ahead.
Yeah, no, I mean, just a couple of things to jump off of that. I mean, so James Spann, because we're kind of walking, you know, sequentially through the supercell. So James Spann's house was hit in that first supercell that dropped a long track tornado from the southwest of Birmingham through like southeast Birmingham all the way to Georgia. Crazy. And then, you know, you just recapped that second tornado, and I'll be taking over the third. But, you know, on the note of fatalities, the one thing that is just terrible with these outbreaks that we get in Dixie Alley, you know, and it sounds stereotypical, but it's the truth. You know, per capita, Mississippi and Alabama have the most mobile home residences per any state in the country, which makes getting the warning out for these type of events in Dixie even more imperative, because when you have those kind of radar signatures and those kind of tornadoes rolling through mobile home parks, I mean, you have no chance. Those are tornadoes that you need to be underground or in some sort of reinforced storm shelter. I mean, these are the upper echelon type tornadoes that rarely happen. And that's what ultimately can lead to a lot of these fatalities across the deep south. So really sad what happened in Ohatchee, because I know a lot of the fatalities were focused around there. But I know we're pushing 12:40 here, so I'll get my screen up and I'll talk about the third and final supercell of the day. So here we go. Get this into present mode real quick. Okay, awesome. Can you guys see my screen?
Yep, we can see it, Andrew.
Perfect. All right. So this was another scatter plot that I hastily threw together this morning as I was getting this conversation ready. Didn't really get the time to shade the tornado reports yesterday by hour, but there were 24 in total. Seems low, but when they were the type of tornadoes that we had, again, makes the high risk very, very well warranted. And really my part of the discussion here this afternoon is going to focus on where I've circled in black in these storm reports. So again, to kind of recap, we've already hit it pretty hard. The wind shear in this environment yesterday was just incredible, both across the deep layer through the depth of the troposphere, but then with the turning of the winds in the lowest kilometer of the atmosphere, just incredible curvature to the profile, just incredibly conducive to rotating thunderstorms. But, you know, one of the things that I think a lot of the cells struggled with yesterday, actually, especially across Mississippi and far western Alabama, is we had no inhibition in the boundary layer. So updrafts were free to go up really wherever they pleased yesterday afternoon. And, you know, if you didn't have a strong enough updraft in a sheared environment like that, there was too much wind shear. These updrafts got sawed off and they really couldn't organize themselves into any sort of mesocyclone before things went upscale and got really messy. So again, we had 3 storms that were able to do it yesterday, but the 3 that did it were able to tap what the SPC called yesterday morning an upper echelon parameter space, which it really was. And once they developed a strong enough updraft to the point where they could organize mesocyclones, they would continue. They would produce a tornado, it would occlude, and then you'd get another meso, it would drop another tornado. And it was really just incredible to watch. So I'm taking you through the 3rd and final supercell of the day. This developed, believe it or not, along the Mississippi-Louisiana border at 3 p.m. Central yesterday, and tracked some like 400 miles from the border of Mississippi in Louisiana all the way to the southwest Atlanta metro area. And interestingly enough, it didn't become robustly tornadic until the very end of its life cycle. And, from what I could see, it was struggling with the wind shear, but it was finally able to organize. And once it did, it really produced a ton of tornado reports, really focused between late in the 2 UTC hour to early in the 4 UTC hour. So, a lot of tornadoes really quickly. So this supercell, if I walk us through here real quick, this supercell, once it went tornadic, cycled 3 times and produced 3 kind of clusters of tornadoes. So this was a screen grab I took of the radar reflectivity right once it finally organized. For the longest period of time as this thing marched across Alabama, you looked in the dual pole and you could see it was rotating, but it was more so just like a shear line of rotation. You really couldn't get the rear flank of the storm to come around and organize into a strong rotating updraft to produce a tornado. But just north of Montgomery, last night, probably around 9:30 Central Time, finally the rear flank was able to organize, and this was the result. I mean, these are textbook images of supercells that you learn about in your radar class and rarely see in nature. So this was the first tornado warning of the day, or the first tornado warning, tied to this 3rd and final long track supercell of the day, was producing a tornado in progress. And for the record, was tracking northeast at 70 miles an hour once it produced this first tornado. So you take that at night, this was probably wrapped up in rain. You can't see it. It's moving at 70 miles an hour. That is just ridiculous. And not surprisingly, in the parameter space such as this produced a tornado very quickly once it was able to organize a mesocyclone and it started doing damage. So I hope you can see my mouse cursor, but I'm pointing out a blue dot to the east of Clanton, Alabama, and then out to the west of Rockford, Alabama. And again, this is the correlation coefficient that Angela kind of went into. In this part of the storm, again, these are non-meteorological targets, as they would be called. This is tornado debris. So this was the first tornado that this supercell dropped. And then really it started to struggle with the wind shear again. I think I might have the winds. Actually, no. Okay, this is right to the second cycle. So it produced that tornado, which was actually on the ground, not for a terribly long amount of time. You're talking 15, 20 minutes. And then it really started to struggle in the deep layer shear again. But then it recycled and organized again closer to the Alabama-Georgia border. This was getting closer to midnight Eastern time last evening. Produced just another ridiculous signature on radar, another very strong tornado. This was the second cycle of this supercell. You can see the reflectivity. This is likely a debris ball just to the northwest of Wadley, Alabama. Reflectivity like this is rivaling that of heavy rain and hail. But from supercell structure, we know that's occurring in the core. This is down in the updraft region. This is likely lofting debris. These are the dual pole winds. We kind of were in a radar gap at this point, so it was harder to resolve the winds, but you can still get a very good sense that there's strong inflow folding around a very well-defined rear flank downdraft. Very clear. There's a strong tornado in progress here. And again, the CC. We saw this way too many times yesterday. Strong debris signature where I've circled it. So this was tornado number 2 of this supercell's lifetime. And then finally, and the one that probably got the most attention, was the final tornado of the night that it dropped once it cycled one more time. For context, we're working into the southwest metro area of Atlanta, Georgia at this point. So this is across the border. It's into Georgia. You can already tell by the structure of this supercell, it's become very elongated south to north. So you can tell, it's really trying to keep itself together, but it's really struggling in that wind shear. But it was able to consolidate and organize one more really strong mesocyclone and tornado that unfortunately pretty much went right through the community of Noonan, Georgia, which is, I think, about a half hour to the southwest of Atlanta. You could tell it was already producing a strong tornado in progress as it was on approach to Noonan, as evidenced by yet another debris ball, really strong rotational signature and the reflectivity. And the dual pole, again, I mean, this rivaled the Brent Centerville tornado. Just incredible inbounds. The Peachtree City radar is not too far off of this screen grab, so we had a pretty good low-level look into this mesocyclone. You have incredible inbounds, incredible outbounds, unfortunately heading right into Noonan, and another debris ball as it's going over Noonan, where we see the pink here, and then just another really tragic correlation coefficient signature. So this thing cycled 3 times, and then really I kind of just want to take a little bit of a deeper dive into why this happened, why we kind of had this last gasp, really violent supercell once the sun had set and we had kind of lost the diurnal cycling. So I'm going to start broad and work in a little more mesoscale. So we'll start here with the 500 millibar analysis from the Storm Prediction Center. Should note that the time steps of this GIF are 18, 21, 0, and 3 UTC. So we're kind of working through lunchtime into the overnight hours here as these storms really started to approach the Atlanta area. And what I'll call your attention to, we've already kind of spoken about it a little bit in this discussion, but there was very, very well-defined baroclinicity at 500 millibars yesterday as this trough moved across kind of the central part of the U.S. up through Missouri and into Illinois. And, you look at this is a very favorable synoptic setup for development of a low pressure system in cyclogenesis, particularly through positive vorticity advection by the thermal wind. And not surprisingly, if we look at the surface pressures at these same 4 times, you can see, this low really gets itself together. It goes from just kind of a broad, diffusely not totally well organized system to very well defined. It doesn't deepen terribly. This isn't a bomb cyclone that we see off the East Coast, but the structure definitely gets its act together as we move through the day yesterday and into yesterday evening. And when you see a rather rapid deepening of a cyclone like this, there better be a strong mass response to support it. And in particular, some sort of southerly flow. So that's bringing, tropical air poleward. And this is exactly what we got as we moved into yesterday evening, as the supercell really started to get itself together in eastern Alabama and then later in the Atlanta metro area. So really struggled on how to best illustrate the mass response that this cyclogenesis event, caused in the low troposphere. But I settled on the mixed layer CAPE because I think it really does the best job of showing how strongly and suddenly mass was drawn poleward as this low deepened across Illinois and then later Indiana. So again, this is the mixed layer CAPE. It's computed over the 1,900 millibar layer. Really, it's just trying to get some sort of accounting for any sort of boundary layer mixing that could be going on. It's still a pretty good proxy for trying to evaluate the prospects of surface-based convection. And again, as we step through these same 4 time steps of 18, 21, 0, and 3Z, you can just see as this low deepens across, the upper Midwest, that, you have parcels and uncapped parcels at that. So the shading again is mixed layer SYN. You basically have an uninterrupted corridor of mass transport that's coming up from the Gulf and then up into the Ohio River Valley, where the center of this low is located at the end of the period shown by this GIF. And, as it pertains to eastern Alabama and the Atlanta metro area, this equated to strengthening low-level southerly flow in an area that was already, I guess you could say, favorable for tornado genesis. And I guess, why is it favorable? Well, because throughout the day yesterday, and now moving to the surface analysis that was done at 3Z last night by the Weather Prediction Center in College Park, Maryland, throughout the day yesterday, there was a lot of shower and thunderstorm activity up across northern Alabama, Tennessee. Didn't really go severe, but there was a lot of rain, a lot of flash flooding, which was the ultimate impact that's going to be forgotten about this event. But what that did is it really worked to restrict this warm front that, is really kind of tied in this very complex structure with the low across the Illinois-Indiana border. So the warm front in particular I'm looking at runs through South Carolina, just to the north of the Atlanta metro area, and then back up into Tennessee. So you had a very strong lower tropospheric mass response coming up off the Gulf, bringing moisture, bringing instability into an area where you have a warm front. And warm fronts, if we remember from the thermal wind relation, these are already hotspots of helicity due to the veering wind profiles that you get along warm fronts due to the warm air advection that's in progress along them. So you had really cool air last night just to the north of Atlanta, believe it or not. So it was about 63 across the north metro of Atlanta as these storms rolled in. You go south of Atlanta near the Peachtree City, Noonan area, it was 74. So across just a metropolitan area, really, you had this warm front that was draped and you had 10 degrees of thermal contrast. So you already have a very favorable low tropospheric wind profile. You have cold air to the north, warm, moist, unstable air coming up from the south. That's going to reinforce this boundary and really kind of make it a spot to watch in terms of supercell development and tornado genesis.
Yeah, Andrew, can I just ask you a question?
Yeah.
Some of the things Angela showed and some of the stuff you're showing now and describing really makes me wonder about a simple experiment a person might be able to run in the modern era of numerical weather prediction. Take the Appalachian Mountains out of the situation.
Yeah.
And just see how much less of a funnel you have for this mass transport right over the Atlanta metro area and eastern Alabama. And for that matter, you could redo the super outbreak, which an anniversary is about a week away now. Mm-hmm. And that was in Xenia, Ohio, places like that, southern Ohio. And it'd be really interesting to see what role does the Appalachian mountain chain have in ushering a narrow channel of extremely moist and poorly stratified air into the Ohio River Valley. In this case, or in that case, I mean, in this case, it got as far north as, Gatlinburg, Tennessee or something.
Yeah, no, absolutely. I wouldn't doubt that it plays an effect. I mean, you see it on the opposite end with cold air damming, in the winter when you get these bomb cyclones off the East Coast. So the Appalachians play a big role. And I wouldn't doubt that if you took that topography out, you probably at least don't get that narrow funneling effect that we saw last night up and into the Ohio River Valley.
Yeah, and it seems to me that's one of maybe several focusing mechanisms that you need in order to really generate something as devastating as this. But I may be wrong about that.
Yeah, I mean, it'd be an interesting experiment to run because I think you would see some interesting results in terms of how that instability kind of broadens out if those mountains aren't there. So yeah, we had this.
I had a quick question about that kind of as well. I was thinking about the mountains, and is the warm front influence, is the location of that warm front influenced by the mountains there? Because I feel like it kind of wraps around them pretty conveniently.
Yeah, that's definitely what I'm thinking. I think it's because of that.
I think that's part, and also there was so much heavy rain across Tennessee and northern Georgia yesterday. It's why they didn't have severe weather. The warm front just could not get further north because there was so much rainfall to the north. So I think combined with the topographic influences from the Appalachians and then just all the rain that they had to the north of the warm front, it really kept it parked pretty much right across Atlanta, which set the stage for the fireworks that ultimately happened last night across the Southwest Metro.
Do you know of any other impacts from the strong storms in the metro area besides that one tornado that passed a half hour south of the city?
Yeah, so there was, believe it or not, there were a ton of flash flood warnings. There were some storms that formed across far northeastern Alabama, kind of north of the boundary. This is kind of taken at a time where the cold front isn't too far behind the warm front. So you've got a pretty strong mass response right along that front, which is kind of shoved the warm front up into Tennessee. For most of the day yesterday, this warm front was parked pretty much through Atlanta to just north of Birmingham. But there were some storms last night as the tornadic activity was ongoing south of Atlanta that formed along and north of the boundary that created a lot of flash flooding, and there were some actually large hail reports as well. But because they were north of the boundary and couldn't route to the surface and tap surface-based parcels, that's pretty much all you're going to get out of storms like that is heavy rain and hail because they can't communicate aloft to the surface. So there were some hail and flooding reports also, but a lot of the media attention is going to be, turned to what happened with the tornadoes. Okay, so then, moving to now just kind of a more around the actual time of the tornadoes time steps. So we're looking at 3 and 4 UTC in these next plots that I'm showing you. So we have here at 3Z, we have the theta E plotted in green with theta E advection plotted in purple. You can kind of see the strong mass response in the cold front approaching from the west. That's shoved the higher theta E up into Tennessee. But you can see a really well-defined warm frontal boundary running right through the Atlanta area. You can basically forget about any surface-based convection north of this tight bundle of theta E lines. And it was really kind of right to the southwest of this really well-defined gradient that the storms went up. This is an hour later at 4 UTC. We've punched kind of higher theta E yet into this area. This is kind of as all hell's breaking loose in Metro Atlanta. So really just kind of, again, shows you where that warm front was. You have some pooling of theta E and instability. But what's really interesting is when you have a boundary such as that parked across the Atlanta area, that's gonna be a natural area that's gonna focus convergence. We already know that's a favorable lower tropospheric wind profile because of the veering of the winds, which I'll get to pretty quickly here. So all those things together creates just a really favorable environment for rotating updrafts. So what you're seeing here is effective storm relative helicity. It's called effective because especially near warm fronts, you can see maxima and helicity that really can't be tapped by surface-based parcels. Some people would call that sucker helicity. So I have effective plotted because this was available to surface-based convection last evening. And for these parameters, it's tough sometimes to create thresholds that are firm, but it's largely agreed in the community that about 250 meters squared per second squared is sufficient for very strong rotating updrafts that are capable of producing tornadoes. And we can see at 3Z across the Metro Atlanta area, we got 400 to 500 meters squared per second squared of SRH, which is just insane. Very, very favorable for rotating updrafts. And this even jumps perhaps a little higher as we moved into the 4 UTC hour. And as these, storms really started to get their act together and producing the tornadoes. So really just a profound, setup and situation that unfolded across Atlanta last night. And the only other thing that I wanted to share here, these are model derived soundings from the rapid refresh model that are provided by the Storm Prediction Center in Norman, Oklahoma. And, the thing I want to really show is the impact of this southwesterly flow and this mass punch that was going northward at the time. So this sounding is taken at 0Z. So this is several hours leading up to the tornadoes in Atlanta. And you can see, you've got a very, nice, well-mixed boundary layer near dry adiabatic lapse rates. The dew point profile is following largely a mixing ratio line, but the CAPE is just not super impressive. We got 680 joules per kg of CAPE at this point, and a little bit of SIN to boot. We've got a nice veering to the wind profile, and that's borne out in the photographs. But thermodynamically, this just isn't looking super impressive. We now jump ahead the 3 hours to 3 UTC, and we can see the CAPE has jumped up by almost 400 joules per kg amongst this southwesterly flow. We've even enlarged the curvature of the hodograph because of this southwesterly mass response. So we've, even created more SRH, more favorability for rotating updrafts, and we're adding thermodynamic support. And we jump ahead 1 more hour to 4 UTC. We're up to 1340 joules per kg in Peachtree City, which was just basically to the south of where the Noonan tornado struck. So you can see over the course of 4 hours, we go from 680 joules per kg of CAPE. This very, very rapid deepening of the cyclone is ongoing in the Ohio River Valley. You get this poleward mass punch, and you can see the impacts of it. Your equatorward of the boundary, you've got 1340. You've gone up almost 700 joules per kg of CAPE in about 4 hours. And the cloud bases have lowered substantially. That's the other thing. So we've lowered the cloud bases. We've added a ton of energy to the environment. This is thermodynamically primed and also kinematically primed if we look at the hodograph and the curvature. So just really profound. It was pretty clear that there was a broader kind of, I don't know if I want to say telekinesis, but process at play where you had the deepening into the low in the Ohio River Valley, and then the corresponding mass response in the deep south that helped kind of lead to this last supercell. So That's pretty much all I have. But just really a tremendous event that will go down in the history books and certainly stands as a great case study for us as meteorologists.
Yeah, that set of soundings was really instructive at the end, Andrew. You can see the not the elevated mixed layer, the low level mixed layer reducing its dew point depression. You know, volumetrically, the dew point depression gets smaller. You could integrate that all the way to the LCL. But I'm wondering if anything happens in the upper levels. It's harder to see that. You know, is it getting cooler at any particular levels? It would be really cool to put those sounding the temperatures above 700 millibars or so on top of each other and see if you're noticing anything going on there, because there might be some cold advection. Doesn't show up so strongly in the winds, but there might be slight changes in that, and 1 degree of cooling is enough to really pump the cape up quickly, especially since the boundary layer is getting thinner and moister. So it's just a beautiful case. You guys have really in one day thought about a whole bunch of great issues here. I think it's going to be exciting to look at more.
Yeah, I mean, I've been looking at this since 9 a.m. So I mean, I haven't even scratched the surface of what we have here. But the richness of this data set, I mean, there's going to be a lot that comes out of this and a lot that we're gonna learn. But again, you know, another shining day for the National Weather Service. They did a great job last week with no fatalities in that lower end event. And then this week, I mean, a lot of these tornadoes again were warned an hour in advance. So just really a tremendous job. So there's a dark side to it, but there's a lot of good that's going to come out of this as well, both from research and on the operational side.
I hesitate to talk about the forecast. We're already at an hour. I'll just say, if you're interested, you need to keep your eyes on a storm that's evolving in 2 pieces. One over Western Canada that seems to be a function of lee-side subsidence to some degree, and that's beginning to organize now. And then another that's related to a really intense, I have to show you at least this. Sorry, I got to show you.
Sorry we took so long, John.
No, that was
we're like throwing all this out at once without having a coherent, like, it was just so much to talk about. Sorry we imposed so much on the forecast time.
No problem. I'll go through this couple of things as quickly as possible, and then everybody can look at what they want on their own. So that's not at all a problem, Angela. That's what we're supposed to be doing, is looking at the most exciting things. So here is I'm trying to make sure I know what time this is valid. Sunday, 12Z, very sharp upper trough coming in off the coast of British Columbia. I want to show you a cross section through this now. Wait a minute. Here it is. Sorry. Right through the base of the trough. Oh, that's a sounding. That's stupid. I'll get the cross section. Hold on a second. Okay. No, I don't want that. How many times must I tell you? Let's see. Very sorry here. I thought I knew what I was doing. I guess I don't. Oh, it's command.
I think it's control or yeah.
Yeah, command. Okay. So here's the PV. Remember, it'll show you where that cross section's taken when we go back to it. It's right through the base of the trough. Now, I just got to point out how far down the 2 PVU gets down to 800 millibars in this thing. This is an extraordinary tropopause undulation and upper front tropopause depression. You can see the baroclinicity, the green lines or theta lines go all the way down to the ground pretty much. So this is a really intense upper feature. I don't want to spend any more time on it because it's going to become the feature of greatest interest. I got to do a new share now. The feature of greatest interest for the development of this storm. And that storm will be arriving in central Ontario, northern Ontario by what time is this? This is now valid 72 hours from now, sometime, 96 hours, sometime on Monday or Tuesday. And so it's down at about 970 millibars. It takes its sweet time getting organized because there's a lee side component to the development at higher latitudes in Canada. And then there is a lower latitude Canada component that's related to that strong upper trough. And that they finally get their act together around Tuesday or Wednesday. They get down to 970 around Churchill, Manitoba, which is exceptionally low for this time of year. And what I've shown you here is isobaric contours of the 300 Kelvin theta E isentrope. So that right to the middle of the storm, you can see this tremendous thermal ridge that comes up here. Here's the warm frontal portion of it over here. And then here's the steeper cold frontal portion of it. The storm does not quite get really deeply occluded. It's weakly occluded. And that must have to do with the deformation of the flow as the wave kind of makes its way into this region. It just can't really wrap up. There's too much stretching along the jet and the upper trough in which it's embedded. So maybe we'll talk about this in retrospect next week, because it's going to be an interesting development, and that'll give me time to understand a little bit more about it than I do right now. But it looks like it's going to be a very intense cyclone development over central and northern central Canada, Hudson Bay, and it's going to have implications for us on Wednesday and Thursday, where we're going to have temperatures drop really down. We're going to have a high, maybe 40 degrees on Wednesday, or I think it's Wednesday or Thursday is going to be the cold day next week. And so a really interesting early spring storm just to our north should make things interesting here in midweek. So I'll leave it to talk more about this next week.
Hey, John, what did I tell you last week?
That's right, Greg. You did say something about this, didn't you? Yeah, there was one more push at least. And wait till you see how cold it is behind this thing. But that might be the last one. I don't know.
It could be. Yeah, but that's what happens when these jets, when the jet intersects and they work their way down, it just causes all hell to break loose every single time.
Yeah, so this is a really nice storm. I mean, it's not unprecedented, but it is rare. And so it's well worthy of discussion. And I'll be able to talk about some things that are not 4 and 5 days out into the forecast, but a little more proximate. I'll bring in Viz 5D next week. So I promise you I'll do that. But Angela and Andrew, thank you so much for a great presentation on a historic event. I hope there's going to be more research done on this in our department. We certainly have the intellects around to do it. That is clear. And in one day, you've turned over some stones that are well worth more consideration. So I hope we can do more on that. And everybody, thank you for tuning in.